Scientists have discovered that our universe is actually very close to flat. But before you picture a giant cosmic pancake, remember, flat in this context is not quite like your kitchen counter. But in cosmology, flat has a deeper meaning, transcending our everyday perception of flatness. We'll explore what flatness means on a cosmic scale and how we can even measure it across billions of light years. Based on current evidence like the cosmic microwave background, the observable universe appears to be nearly flat on large scales. This means that on a very large scale, the geometry of three-dimensional space resembles a Euclidean plane rather than a positively curved space like a sphere or a negatively curved space like a saddle. When we say the universe is flat, we are not talking about how it looks. Instead, this flatness means the rules of Euclidean geometry hold true on large scales. The sum of angles in a triangle still adds up to 180 degrees. Again, the flatness, we are talking about the absence of curvature, not a definite form, not like a sheet of paper. Studying the curvature of the universe helps us comprehend its origin, evolution, and possible future scenarios. Questions about its expansion, whether it will continue indefinitely or eventually collapse, and whether it's finite or infinite, all connect to its curvature. The flatness problem is a key puzzle in cosmology revolving around the density of matter and energy in the universe. This density plays a crucial role in determining the overall curvature of space-time. Imagine space-time as a vast fabric and matter and energy as the weights that bend and shape this fabric. If there is too much matter and energy, space-time will curve inward, leading to a closed universe, like the surface of a sphere. Conversely, if there is too little matter and energy, space-time will curve outward, resulting in an open universe like a saddle shape. The critical point lies in achieving a perfectly flat universe where spacetime isn't curved in any direction. To achieve this, the density of matter and energy must be finely balanced to a specific critical value. Now, here is where the mystery deepens. The observed density of the universe appears to be remarkably close to this critical value. Let's look into the compelling evidence supporting the flat universe hypothesis, such as the uniformity of the cosmic microwave background radiation, the large-scale structure of the universe, and the predictions of inflationary theory. Let's look at each piece of evidence one by one. The primary evidence supporting the idea of a flat universe comes from observations of the cosmic microwave background radiation. The cosmic microwave background is the afterglow of the Big Bang, and it provides a snapshot of the universe when it was just 380,000 years old. The measurement taken by WMAP and the Planck satellite show isotropy, which means they look the same no matter which direction you look. This means the average temperature of the CMB radiation is almost the same across the entire sky, regardless of the direction we look. If the universe were curved, light rays traveling from different directions would have experienced different paths and picked up different temperature signatures. This would lead to distortions in isotropy, non-uniform fluctuations, deviations in the power spectrum. As we'll see, the strong concordance between observation and the prediction provides compelling evidence for a flat universe on large scales. In a curved universe, these fluctuations would be distorted in specific ways, but such distortions haven't been observed. This uniformity strongly supports a flat universe. The figure illustrates this situation with two possible outcomes. The red lines indicate straight light paths to us from opposite sides of a typical hotspot in the CMB, as would be the case in a flat universe. The gray lines indicate corresponding curved light paths as they would appear in a universe with negative curvature. The temperature fluctuations in the CMB are typically decomposed into spherical harmonics, which represent different angular scales. In a curved universe, the power spectrum of these multiple moments would exhibit characteristic deviations from the predictions of a flat universe. We use the locations of the main peak in the temperature spectrum to determine the average apparent spot size. In a flat universe, the main peak occurs at multiple moments around 220, while a negatively curved or open universe has a peak farther to the right and vice versa for a closed universe. A central feature of the microwave background fluctuations are randomly placed spots with an apparent size of 1 degree across. By comparing the apparent size of the spots, which is about 1 degree, to their known actual size at the time of recombination, we can determine the geometry uniquely. Precise measurement by satellite like WMAP and Planck reveal incredibly uniform temperature fluctuations in the CMB, precisely what we would expect in a flat universe. Any curvature in the universe would distort these fluctuations in specific ways, but such distortions haven't been observed. This uniformity strongly suggests a flat geometry on a grand scale. The second evidence of a flat universe is large-scale structure. Galaxies and galaxy clusters are not randomly scattered across the cosmos. They form intricate patterns, revealing clues about the universe's geometry. Surveys like the Sloan Digital Sky Survey, SDSS, have mapped the large-scale distribution of these structures, and the observed patterns of clustering and voids align beautifully with what we expect in a flat universe. The SDSS is the most ambitious astronomical survey ever taken. It provides a three-dimensional map of about 1 million galaxies and quasars. The third evidence for a flat universe comes from inflationary theory. This leading cosmological model predicts a flat universe as a natural consequence of its rapid expansion phase shortly after the Big Bang. Inflation is an extension of the Big Bang theory, in which the universe expanded from an atomic scale to a cosmic scale in a fraction of a second, making the universe geometrically flat. This rapid expansion, as you can imagine, would leave its stretch marks on the cosmic microwave background. Inflation was one of the prime theories that WMAP tested. Imagine space inflating dramatically, ironing out any curvature on large scales, and leaving behind the flat geometry we observe today. Inflationary theory provides a robust theoretical framework supporting the flat universe hypothesis. Note also, calculations based on inflation theory predicted this angular size to be around 1 degree across the sky. So, while inflation theory doesn't predict a single fixed level of flatness, it suggests that the universe should be significantly flattened compared to its initial state. The observed near flatness of our universe strongly supports this prediction and continues to be an active area of research in cosmology. Technological advancements have refined our measurements of the universe's curvature. Based on the 2018 results of the Planck mission, the curvature parameter of the universe, omega k, is tightly constrained to be very close to zero with a value of 0.0007. Now we know what does the flat mean when cosmologists refer to the universe as flat. They are not talking about the shape, but the curvature, which is about geometry. Again, while the term flat might lead us to imagine a 2D plane, the flatness of the universe in cosmology refers to its curvature on a large scales, not its shape. There are actually a few candidates for the shape of our flat universe. The first one, obviously, the infinite Euclidean space. This is the most common visualization, a boundless and infinite space where parallel lines remain parallel forever. However, this can be difficult to conceive on cosmic scales. The second case is 3 torus. But let's think about 2 torus first. It's a 2-dimensional version of torus. It exists in 3 dimensions and can be visualized as a donut or a tire tube. Yes, a 3 torus is indeed considered one of the candidates for a flat universe in a certain cosmological models. A 3 torus, also known as a cubic torus, is a 3-dimensional version of the 2 torus. It's a donut shape extending in all 3 dimensions. It can be visualized as a cube with opposite faces identified and connected, forming a toroidal shape in 3 dimensions. Like a flat universe, a 3 torus has 0 curvature. 3 torus has a toroidal topology, similar to the 2 torus, but in 3 dimensions. This means that it can be finite but unbounded, allowing for the possibility of a flat universe that wraps around itself in 3 dimensions. The third candidate, there are other 3D manifolds that are candidates for our flat universe. Mathematically, other closed, finite 3D shapes with 0 overall curvature can also represent a flat universe. These shapes might be more complex and harder to visualize, but still satisfy the flatness condition. In conclusion, our exploration of the concept of a flat universe has shed light on its profound implications for the future of our cosmos. As we've delved into what it means for space to be flat, we've uncovered the intricate balance required for such a state and the mysteries it holds about the fundamental nature of our universe. Through the compelling evidence provided by the cosmic microwave background radiation, the intricate patterns of large-scale structure, and the profound insights of inflation theory, we've glimpsed the remarkable consistency of our observations with the notion of a flat universe. Yet, our journey doesn't end here. The quest to refine our understanding and unlock the universe's deepest secrets continues unabated. With each new discovery and technological advancement, we inch closer to unraveling the mysteries of our flat universe, revealing hidden elegance and profound connections between the vast expanse of space and the fundamental building blocks of reality. As we stand at the precipice of discovery, let us remain ever curious, ever determined, and ever inspired by the wonders that await us in the boundless expanse of the cosmos. Thanks for watching. If you found this video helpful, give it a thumbs up and don't forget to subscribe to the channel. Let me know in the comments what other topics you'd like to see covered, or if you have any additional tips to share.